Okay, so what's the difference between Arrhenius, Bronsted, Lowry, and Lewis acids? Well, an Arrhenius acid is a substance that produces H plus in solution, which means it produces protons. And usually we're talking about in a water solution, in an aqueous solution. A Bronsted Lowry acid is an acid that produces, or we should say, donates protons. So this definition is very much like an Arrhenius acid. And a Lewis acid is a substance that accepts a pair of electrons. So let's see some examples. Now I listed here 4 different types of acids, and we're going to figure out which category these acids are in. And some of these substances can be in 2 categories, all 3 categories, or only in 1 category. So let's figure it out. The first one is hydrobromic acid. So, as we know, hydrobromic acid, if you have that in water, I'll draw water like this so that you can see what's happening. That's in water. Water is now acting as the base. And so this electron pair of water will be attracted to that proton. The 2 electrons that are binding hydrogen and bromide together will stay with the bromide. And so what you'll have as the products are your hydronium ion and then you'll have the bromide anion. So this is the bromide anion because it has a negative charge. So here we have our hydronium, which has a positive charge. So this is what hydrobromic acid does in solution with water. So does it, number 1 for Arrhenius, does it produce a proton? Well, it does produce a proton because that proton is the one that attached itself to the lone pair electrons originally from the oxygen. Actually, written here, it's this pair of electrons. So yes, it is Arrhenius acid. Is it a proton donor? Yes, it is a proton donor. Almost the same definition as Arrhenius definition. Is it a Lewis acid? Did it accept a pair of electrons? Yes, this proton accepted a pair of electrons. So HBr is all 3 types of acids. Okay, so let's now look at ammonium chloride. So as you know, ammonium chloride is completely soluble in water. So even though we write it out like this, it completely dissociates into ammonium ion and chloride ion in water. Again, just to review, what does aqueous mean? Well, that means in water, the negative dipoles of water attract the ammonium ion, and the positive dipoles of water attract the chlorine. So this is what we mean by aqueous, just for review. All right? So then that means that this is our acid form of ammonium chloride. So this is the acid coming from ammonium chloride. This now will react with a water molecule in this way. Again, the lone pair of electrons here will be attracted to one of the hydrogens in ammonium. Okay, so I wrote it out a little bit better here. So one of the electron pairs on oxygen is going to be attracted to this hydrogen. These two electrons here will stay with the nitrogen. So now your product is your hydronium cation. And plus your ammonia. Okay, so let's figure out now if ammonium chloride or the ammonium cation is an Arrhenius, Bronsted, or Lewis acid. So an Arrhenius means that it produces a proton, which it did. It produced a proton, which is going to be in the form of a hydronium cation. That's our proton there that was formed. So it is an Arrhenius acid. Is it a Bronsted Lowry? Yes, it donated a proton to the base being water. Is it a Lewis acid? Was it a electron pair acceptor? Yes, this species accepted a pair of electrons, so it is also a Lewis acid. So now let's look at boron tribromide. So here's our boron tribromide, little structure. Okay, so if this was, let's say, with another bromide anion, so what does it do? So again, boron is electron deficient because it only has 6 electrons around it. It's one of the few elements in the periodic table that can be stable with 6 electrons around it, meaning it does not follow the octet rule. But if there is an anion in the vicinity, it definitely will react with it. So this pair of electrons then here will be attracted to the boron, forming this boron tetrabromide molecule. This will have a overall negative charge because it added an electron pair. So now let's check if this is an Arrhenius, Bronsted, Lowry, or Lewis acid. So an Arrhenius acid, did it produce a proton? Actually, if you look at this equation, there are no protons produced. There is no H plus here in this entire equation, so it is not an Arrhenius acid. Did it donate a proton? Again, it did not. There was no protons produced or donated. Is it a Lewis acid? Did it accept a pair of electrons? Yes, it did. It accepted a pair of electrons. And so that it is a Lewis acid. Now let's look at the last type of molecule. So this is a methyl cation. It's very unstable. So it's a methyl cation or a carbocation. for the organic chemists. Anyway, let's see when it is around water, how does it react? Again, water is our base. This is, of course, our acid. So the electron pair on water is going to be very much attracted to this. It's a very fast reaction. So our products are going to be this, and there's a positive charge on that molecule. Okay, so this is our product. So is this acting as an Arrhenius acid? Well, it did not produce a proton. The protons here were from the water, so it did not produce a new proton. No proton was produced. All the protons that you see here have come from the original origins. So it is not an Arrhenius acid. Did it donate a proton? No, it did not donate a proton. No proton was produced. Is it a Lewis acid? Yes, it accepted a pair of electrons. It accepted this pair of electrons. So it accepted a pair of electrons, so it is a Lewis acid. Okay, so what was interesting about the last reaction is that I wrote down the product from the last reaction, which is this molecule right here. The product from the last reaction, let's figure out if that's what type of acid that is, because that is an acid. So looking at this, when we have water as obviously the base, let's see what happens. Well, does it produce a proton when it reacts with water as the base? Well, it does, because when this lone pair of electrons, let's say this one here, is now attracted to this proton, and these lone pair of electrons stay with this oxygen, we actually form these two products right here. So we do form our hydronium cation, which is this guy here. So we do form a proton in solution. So it is an Arrhenius acid. So this is an Arrhenius acid. Is it a Bronsted Lowry acid? Yes, because it donated a proton. It donated this proton. So it is a Bronsted Lowry. And is it a Lewis acid? Well, definitely it is, because this proton accepted a pair of electrons. It accepted this pair of electrons. So it is also a Lewis acid.